Good afternoon and welcome to the session on clean heat and power applications. My name is Eleni Kontanasiou. I'm project officer at the Clean Hydrogen JU. And while in this morning, I try to give you an overview of the projects that they have been funded under this area from the JU. I don't think that there is a better opportunity, that it's much better to hear about the advancement of the project, their main achievement and their main challenges from the persons that they are implementing this project. So I'm very happy that in this session we will have 6 projects to be presented. They come from the different areas, all related to clean heat and power applications. However, these projects, they come from different technology readiness levels. So we have projects on the low TRL and also on innovation, action and demo activities. And also we have as discussed this morning, the 2 projects that they have started very recently, just a few months ago, on gas turbines. So I will not take more time. I will give the floor to the first speaker, who comes from University of Salerno, Professor Cesare Pianese, who will introduce to us RUBY project. RUBY is the acronym of Robust and Reliable General Management Tool for Performance and Durability Improvement of Fuel Cell Stationary Unit. Professor Pianese will let us know of what has been developed under the project and about the RUBY tool. Cesare, the floor is yours. You could share your presentation. Thank you. We can see you now. Okay, and your presentation is loading.
Okay.
Yeah.
Okay. Good afternoon. Good afternoon. Sorry, I have to activate the pointer. Just 1 second. And yes, it should work. No, doesn't work. Sorry. Yeah. Okay, I'm ready. So good afternoon again. Thank you, Eleni. I'm Cesare Pianese. I'm the coordinator of the project RUBY that has been introduced by the project officer. So the project has been funded in the call of 2019, and the objective of this topic was the enhancement and durability and reliability of stationary PEM and solid oxide fuel cell through advanced diagnostic and control tools. The project started on the 1st of January 2020 and is going to finish at the end of next year. We are almost at 80% of the implementation today, and the project budget is roughly 3 million euro. We are 11 partners from 7 countries that are shown here. We have industries like Bitron, which is a company from electronic equipment areas. Then we have Sunfire and Ballard, and then the others are university and research centers. Actually, we have some support from another university from Switzerland, and a company providing natural gas to the grid, and a spin-off university from University of Salerno. They are supporting the activity in the last period. The main objectives of RUBY are reported here, so are 4 mainly related to the improvement of performance and durability, which is the main topic of the call. The topic design engineer the hardware in order to perform these monitoring, diagnostic, prognostic control actions on the system, and then of course the experimental campaigns that are required for the characterization, and finally for the testing. And then one objective is to develop some functions that could support the advanced management when the systems are introduced in the smart grid, and also to improve the maintenance. And basically we work on algorithms for diagnosis, prognosis, control, and mitigation actions. on the hardware in order to use and then we are using technologies that can be, useful for scalability at industrial level, and of course, typical experimental in labs and testing in a real environment. And then finally, the objective is to analyze supervisory for remote monitoring action towards smart grid, as I said before. The summary from the activity point of view is reported here. We see the main functions here in terms of algorithm implementation, which is related to the first algorithm, then the hardware for the tool, which the acronym is MDPC, and then we have the reference as systems to be modified, and particularly the power electronics in order to perform advanced diagnostic that will be mentioned in a second. And then in order to have a good experimental campaign, we designed the experiment in such a way to maximize the information taken from the experiments and also to have a better testing. And here, this is the fourth objective in terms of overall management, and indeed it is linked to the smart grid interface, the remote monitoring, and the predictive maintenance as objectives. So basically, we started from a state of the art that was growing in the last 10 years in the area of diagnostics and control, and particularly we had some experience, almost all partners, in terms of development of advanced algorithm and tools. And basically, the key points are the possibility of performing electrochemical impedance spectroscopy on the real system, so move the EIS from lab to real field, and also the real-time optimization, which is a sort of control that is based on the current status of the system. And this is applied on system for implementation on field. And then we started from the know-how developed in the past with respect to hardware and advanced hardware for power electronics applied to fuel cell. The application and market area are stationary fuel cell and electrochemical devices as direct application, but we see potential use for automotive and batteries as well. So the key concept is based on the implementation on field of EIS and real-time optimization. On the right side, you see the two schemes for the SAMFILE micro CHP system that is being used in the project, and then another backup system for PEM, and then what is the main activity we have done in terms of hardware. So we designed a special DC-DC converter that allows to perform perturbations that are felt by the two stacks, and this is the same equipment. Of course, in this case, these are low power systems, so the range of voltage and current are compatible together, and then we interface this DC-DC converter in the micro CHP to the DC-AC, so the inverter, and then it's connected to the grid. And in this case, in the case of the backup system, we use only the DC-DC system in order to perform the perturbation and then the connection on the load with the load to the other side. And then on the electronic control system, on the electronic control unit and management system, we introduce this red box, which is the so-called Ruby box, which is the board in which we develop, implement the algorithm, and we develop the way how to control the converter and to perform the diagnosis and the control and all functions. So as we said, the objective is to improve performance and durability and to improve the management through advanced functions. So the key functions implemented on board are advanced stack monitoring via electrochemical impedance spectroscopy, then the stack diagnostics via EIS, and then also we analyze the balance of plant component condition monitoring, balance of plant fault detection and isolation, prognostics for stacks in order to identify the remaining useful life, and then the real-time optimization, as I mentioned already. And the idea is also to provide useful information in order to mitigate the effect of degradation, for example. So we have 4 main achievements. This is related to the testing activity. We have 32, we have for sodium oxide, 10,000 hours of operation in nominal and faulty condition is at the lab of VT of CA here on the right side, and also at VTT on system. So we have for sodium oxide 32 EIS spectra measured on the module, and then 700 hours of hot module operation with the 74 EIS spectra. Then for PEM, we have 3,800 hours. The system runs for 1,000 hours in nominal faulty condition with more than 100 EIS spectra measured. And then we built a database of features for monitoring and diagnostics from EIS spectra. So this is, for example, on the right, one example on PEM stack, and this is on solid oxide, and this is a time series that have been recorded as CA. Then the second achievement is in terms of algorithm. So we have EIS diagnostics, the use of equivalent circuit modeling, for parameter identification from the stack, the balance of plant diagnosis. We use also machine learning recurrent neural networks in order to have direct monitoring of the voltage on the field, and then the support of multi-scale analysis for solid oxide in order to better understand some phenomena like degradation, and also the state of health with advanced models, and also the RTO, which takes into account the current constraints or the constraints imposed by the users. Then for the hardware, this is the main configuration. So this is the Ruby box, so in which we have a Raspberry Pi, which is the main computational module that orchestrates on the system. Then we have a full Ethernet communication, and an analog front end, which is which gets the measurement, the data that are measured on the real system. And then this is the DC-DC converter that has been that will be outsourced by Coastal company, German company, and they will be fit on the real system from PEM and for some file micros HP. We use algorithms that have been developed in open source languages, and then we are also getting the support of a third party like this company Minervas that has a patent from University of Salerno, and then from HSSO, which is a university in Switzerland. Then the last achievement is the implementation of the 2 solid oxide micros HP systems on the Gaznat here in Switzerland. Is a real site, so we will not pay likely the gas that we are going to use, but and then we will use this system in a real environment, and this is within the lab of the VTT in operational conditions. And then on the right side, the tests on PEM at AFER. So the risk that we faced during the project are reported here. So we had the problem of pandemic that limited the interactions. So then we were able to increase the remote interaction, and then to supplement some data from previous project with experiments in terms of EIS and long run in order to develop the algorithms. We had one problem with one partner that left the project, and in 5 months, thanks to support of the JU, we were able to get on board Sunfire, and we are very grateful to Sunfire who trusted in our project, and of course in support of Eleni and her colleagues before. And then also there was a risk in terms of shortage for electronic component during pandemics, but luckily this problem was overcome. Otherwise, it would have cost more the device. The device actually, in terms of Ruby box, will cost as target of the topic less than 5%, sorry, of the overall cost. Then the challenges were to adapt the experimental activity to the new Sunfire system. So we had to run fast in order to have new experiment from another system. Then the new scheme of the DC-DC converter in order to fit in both systems was not easy to identify the configuration. and then also the topology, reconfigure the power electronics in order to perform the EIS on the stack. And then the final decision, we actually were able to outsource a low-cost DC-DC converter. Really low cost, is less than 1,000 euro, even less. And then also the implementation of conventional commercial systems, at least at this level, of course. For advanced implementation and commercialization, Raspberry Pi will be substituted by other devices dedicated to this function. And then we have full Ethernet communication, which is very useful for remote control. In terms of exploitation, with respect to the activity, of course, Sunfire will explore the integration of the converter and implement this MDPC tool in their device, and they are working in this direction. Vitron, which is the supplier of the hardware, the development, who is developing the Ruby box. Of course, they are interested in exploiting this solution also for energy meters, for example, for electric vehicle charging station and other electrochemical device, of course, other than the potential application for fuel cell. EPFL is working with the SSO. They identify in the frame of innovation radar a path in order to have the exploitation of RTO algorithm. UNISA, Vitron, and this startup from University of Salerno, we are seeing the possibility to develop the Ruby box with implementing, at least for the moment, one of the patents that is available, but of course there is room for other algorithms according to the needs for and the interest for the other partners. We also, as University of Salerno, we participate in this program funded by the European Commission, which is the Intellectual Property Booster, and then we started already some analysis on how to exploit the solution. The impact is reported here on the left. We developed a lean business canvas during the preparation of the proposal, and then the improved performance availability. We expect a reducing total cost of ownership, help to market penetration thanks to the improved functions, and then a better management with the EIS and RTO function in order to improve remaining useful life according to where the figures that were considered in the topic, and then to keep the average efficiency thanks to RTO function at 35% until the end of life, increase availability, and reach 15 years of operation. And as I said, the fourth objective is to help predictive maintenance and a better integration in smart grids. With respect to communication, we already organized 2 workshops with more than 50 people in presence that attended both workshops. Then we have 28 presentations that are available on the website of the project, so you can go there and then you can get the material. All participants coming from 10 countries. The participants, they were from 6 companies and then research and university. They were organized in Lucerne and the second one last September in Capri during 2 interesting and important events at the international level. So these are just a few images. We are on the left here, the brochure we developed. On the center, there are 2 copies of the newsletter we sent. On the top, there are some participants to the first workshop, and this is the will be roll up at registration of the conference in Capri. Then this is the last slide. So we prepared 12 papers on applied energy, electrochemical transaction, journal power sources, IEEE transaction. We had 5 presentations, 6 conferences. We have 55 deliverables, each has a public version of 1 page. Then we have 9 public deliverables available on the website, and then the extended periodic report will be public, available on the web. And then we also added we were very lucky to have 18 students and thesis developed, 4 PhD students, 8 masters, 6 bachelor. So this is the end of my presentation. Thank you for your participation. That's it.
Thank you very much, Cesare. Thank you for the clear overview of the project and working on the background, I would say, of the technology to improve the performance of the lifetime of fuel cells. Maybe research innovation actions, they are not as visible as the innovation action, however, they are equally important. And after this presentation, we will go now to an innovation action and to remote project on a remote area energy supply with multiple options for integrated hydrogen-based technology. And we will hear from Professor Massimo Santarelli from Politecnico di Torino about this project.
Hello. Yeah, I'm here. Hello. Can you hear me?
Thank you very much. The floor is yours. We can see your screen. So.
Yeah, thank you. So can you see my presentation, I think?
Yes.
Okay. Thank you, Eleni. So yeah, thanks you for the presentation, the introduction, and yeah, this I'm Massimo Santarelli from Torino, Politecnico of Torino, in Italy. The project is named Remote, which is connected to the use of hydrogen-based system for storage of medium size, let's say at the moment, storage system based on hydrogen for remote community. I will give you some details of the project. Then we will see the result. So it was a call in 2017. So quite old. We started in 2018. But at the end, we ended at mid of this year, so in end of June of this year. It's been quite long. Why? Basically for COVID period, but also because we had some trouble in the sense that some demonstrator has been replaced by other demonstrator. At the end, fortunately, we have found all the demonstrators that were supposed to be developed in the project. So the stage of implementation is 100%. We concluded a few months ago, and the budget was around 6.7 million euro with a contribution of 5 million euro from the FCAJU, Clean Hydrogen Now. Okay, so these are the distribution of the partner. So we had 11 partners from 7 different countries. You can see many countries involved from Norway to Greece and Spain, France, Italy, Belgium, Denmark. Yeah, these are all the countries involved. Both technology provider like Ballard, like Hydrogenics, some integrator like Unicom, like to Power System, some like the last one is basically Powidian, and some end user. In this case, were ITC, Capisa, Trondheim Energy, and Horizon in Greece. The rest was a European research institution like CERT, Politecnico, and I think is completed, and Sintef. Okay, so many partners. It was coordinated by Politecnico, by me. Going on. Yeah, which was a topic. We are talking of remote communities based on local renewable. So this is the topic: variable local renewable. Let's say wind, photovoltaics, to supply a local community. What can be done? Can be done something related to a power-to-power solution of storage. Of course, if we are talking to a community, it's something that is a medium, big, going to big size, and also in terms of storage period can be seasonal and not only day and night, something like this. So probably batteries are not enough in terms of capability to do this job. In this case, the chemical molecule can complement, more than complement, I can say, can take the leadership probably of the storage, complemented by batteries. So the system is a power-to-power system based on batteries as a support, but mostly based on hydrogen. So electrolyzer, hydrogen storage, and fuel cell. This can do the job. So can do the job in terms of replacing what is normally used. So diesel engines, many cases already, old system and very polluting, but also in some cases, very expensive, because to supply diesel, so a fossil produced somewhere in the world, to a local community in Europe, but also in other places, will be the same, can be very costly already now. So we are not talking of a center of a city. So the infrastructure to supply this diesel in a remote condition, like an island, can be already now costly. Or you can have a good connection when feasible, because we are talking of a remote community in some cases. But anyway, even the grid, we can talk of installation costs, which can be very high. The work can be also impacting outages sometimes. So probably already now a very good solution can be the local storage. So power-to-power system, they can obtain this job, this result at the end, to decrease the local pollution, also the global, but especially also I can say especially the local, so no emission locally. This is an interesting point. Reduce the local cost of electricity, because in this particular application the cost can be really high because of the difficulty to supply even the fossil. To enhance the energy autonomy, so not to be dependent on outside fuels, and also to improve, let's say, the reliability of the service. So this was the aim of this project, to demonstrate that these assumptions were true. So yeah, I think we demonstrated. We did in the project a free demonstrator at the end. So the system is, as you see, based on local renewable, local load, and the storage system based on battery, but dominated by the hydrogen system. This we have done in 3 different sites. One in Trondheim, you see in Norway, with a system of 100 kilowatt load. I will give you the more detail later. One in Ajkistro, so in the border between Greece and Bulgaria, with a load of 50 kilowatt. And the last one in Ireland, in Gran Canaria, in Spain, in the Canary Island, with a load of 100 kilowatt. So you see, the system is not we cannot say big size, but is medium size, but already significant. So to demonstrate that the system really works and really operates as expected. The next step probably will be bigger size, but anyway, also these sizes are very used in Europe and out of Europe. So this medium size can be still an element of interest. Going more in detail, so you see here the demonstrator that we did in Norway. So technically the system was based on renewable, was in this case a can say small size PV plant of 85 kilowatt. You see here in the picture. Plus a wind generator of 225 kilowatt. You see here again in the picture. This has been used to assure a local load, which was agri-food industry, using this storage system that you can see better in the bottom, composed of an electrolyzer, which is a PEM electrolyzer, a PEM fuel cell, in between, so PEM fuel cell system, in between the hydrogen storage you see in this storage cylinder. All this has been based in terms of size with a electrolyzer of 50 kilowatt PEM, gas to power, so the fuel cell of 100 kilowatt, again a PEM, a storage of 37 cubic meter, a 30 bar. Why so low the pressure? Because you see there was no problem of space availability, so we decided not to compress the hydrogen after the electrolyzer, so 30 bar of storage. Complemented by a battery of 550 kilowatt hour in lithium-ion chemistry. The biofuel generation was just as a complement in case of need, but basically we never used it. So I can show you something in terms of operation. The system was really dynamic. We are not talking of a system in nominal point of operation. So you can see an example of a night and day in February 2021 in Norway. So you see, during the night there is no sun, of course. The wind is this blue line, light blue line. So not so much wind. So first, during the night there was a discharge of the battery. Below the 30% of state of charge of the battery, we decided with the control system to insert the fuel cell. So the fuel cell went in operation at 40 kilowatt and remained in operation at this level in order to supply the load. At the same time, thanks to the wind, the battery was recharged partially So you see there was a recharging of the battery, the red line you see on the bottom. So at a given point, we decided to discharge again the battery, and so to save energy from the fuel cell. And all this for all the night. So you see the dynamic operation of this system was not in nominal point, so always changing. In the day, the sun, when raised up, so the sun was able to recharge the battery, so also to supply the load at the same time. So the battery was recharged partially, and the fuel cell went back to the lower value of operation, 20 kilowatt, and so on and so on. This is just an example of our operation that has been for the complete 2021, night and day and night for the complete year, in this dynamic way. So, I mean, I think a very good achievement in terms of technological development and demonstration of the concept. This was the installation in Greece, quite different, because in this case, the system was based on local hydroelectricity. So the system was basically a backup solution. You see the electrolyzer is an alkaline typology of 25 kilowatt, so smaller, of course, compared to the case in Norway, because of the larger availability of the hydroelectricity. The gas to power, so the fuel cell was a PEM fuel cell of 50 kilowatt with a small storage of 12 cubic meter at 30 bar of compressed gas, and a small battery of 92 kilowatt hour, still lithium ion chemistry. So you see the plant is smaller. Why? Of course, because the availability of the hydroelectricity is higher compared to the availability of wind and photovoltaic. So the size has been optimized according to this. Anyway, also here we did a continuous operation. You can see the system. I can see also very elegant in my view of the organization of the plant. Basically, the efficiency we have seen along the year, of course, changed the point of operation. But you see the fuel cell. The electrolyzer achieved the efficiency that were between 50% and 58% of efficiency along the different months. The fuel cell was operating again in different point of operation, but between 43% and 51% of efficiency along the year. The round trip efficiency, of course, depends again according to the type of month. It is you see a mixture between a roll of battery and a roll of the hybrid fuel cell and electrolyzer, so the chemical part, which is the hydrogen. And again, so the value of the round trip can be very variable. So from let's say 50%, 58% to something close to 90%, depends on the fraction of use of the hydrogen and of the battery. So anyway, good level of efficiency, I can say, in the round trip, but also considering that these are renewable, otherwise we are curtailed, so they are used to supply the load. Last one is the installation in Spain. You can see in the Canary Island. This was the last installation. It has been done in a second part of the project. The system is based again on photovoltaic and wind. You see it is placed in the Canary, in Gran Canaria, in La Aldea. So based on photovoltaic and wind, the electrolyzer, 80 kilowatt of alkaline electrolyzer, and the load again 100 kilowatt of PEM fuel cell. Storage in this case is in terms of kilogram, so 50 kilogram at 200 bar. So higher storage, in this case there is a compressor, and 200 kilowatt hour of lithium ion battery. Here I cannot show the data because we are elaborating this data because it has been the last installation, so we need more an higher amount of data to show you, but it will be in the deliverable, of course. Some consideration in terms of result. The result has been good in terms of technological achievement. We did 13 months in Norway, as you see. We did around 2 years in Greece, around let's say 6 months so far in Spain. And for example, in terms of CO2 save, CO2 all included. Also is a LCA. CO2 is a CO2 equivalent. So the remote scenario allowed to save just in Norway around 1,000 kilogram of CO2 per megawatt hour produced. So of course there is no emission. Also, consider this type of system you can see on the bottom. If this system, for example in Norway, should have been based only on batteries, the cost of the electricity will be increased so much. You see, this is the value. Compared to the hydrogen solution, the hydrogen solution, in place of having only a battery, is already now economically better. Is only better compared to the cable. So to connect an island with the mainland, to the main grid of the mainland, using a cable. So you see the cable, how much is the cost, and how much is the cost of the solution that we had in remote. So is good for this type of application already now, economically. What we have achieved also, now we have completely developed models, so modeling the same tools for calculation optimization of this type of system. In fact, we are using a lot, we are very required now. The next use will be probably to the design of Hydrogen Valley. We are now involved in 3 Hydrogen Valleys as a partner, and we will use this tool that we have developed in remote to design in an optimal way this type of system. So we have developed a tool for multi-objective optimization. We use a mixed integral linear optimizer that can optimize at the same time the cost and the emission. So we have all the tool to design let's say a valley. So anyway, a system where the hydrogen is used for storage, for mobility, for industrial use. This is a very good achievement of the project that we are going to use a lot. Next step, after the project, this is a result of request. We have demonstrated now that the system can work at intermediate scale, so below 1 megawatt. Now the requirement that we receive are bigger size. There are a lot of requests for free solution in remote island, remote area like in the Alps, microgrid. Some districts in some municipalities are considering this type of system. Some, how do you say, the system local system that want to rely only on local renewable. So now the next step will be with the technology provider to move from let's say the size of 1 megawatt to something more ambitious, something that go to 10 megawatt to 100 megawatt. This is especially to explore this type of system out of Europe. In fact, even only considering the remote communities. So of course, I think the market of this type of system is much bigger than only remote community, but also even only consider a remote community at the end, which are most of them are based on local diesel generator. You can imagine we are around 750 million people living in this type of site around the world. So it's not a niche market, let's say, for hydrogen system in this case. And we can consider that this can save at the global scale around 1.5 gigaton of CO2 per year, even only considering a remote community. So I think this can be anyway, even only consider remote, a good possibility of market for European technologies. And the dissemination, we did several activity in terms of conferences. The last conference has been done in Canary Island in École in June. We produced a paper. This one, École 2023. We produced a paper as usual, and we won two, a big award. I say one was the European Sustainable Energy Week Award in 2020. It was the first winner, the winner of the Innovation Award. Last one was basically 2 weeks ago. It was in this in Oslo. Award supplied by the Svalbard Institution of Research, because they are interested to implement this type of system in local community like Svalbard or like north of Canada for native people that lives there, and also for a local automatic remit station. So now we will produce an automatic remit station based on this type of hybrid system using hydrogen. Okay, so I think that this is at the end of my presentation, some picture of the group, and thanks to the group, because it has been really a nice project for us. Thank you.
Thank you very much, Massimo, for the nice presentation, and thank you very much for the work that you have done under this project. You explained a bit at the beginning the challenges that you have, but at the end, I think you had 3 successful demos with happy, let's say, end users, and I hope that we will have the chance to talk more about this project and what it can offer, let's say, to the wider, let's say, community at the Q&A session at the end. So, Thank you very much.
Thank you.
We will go to one more innovation action. We will go to PACE project, if I'm not mistaken. No, okay.
Should be me, I think, Eleni.
Okay, it's okay. I used the previous agenda, so thank you very much. So actually, we move again from an innovation action to a research innovation action, which I would say, however, that it has many elements of being an innovation action. The coordinator Jan van Herle from EPFL will let us know of also the demo activities that they have been performed under this project. We talk about waste to WATTs, about unlocking the unused bio-waste resources with low-cost cleaning and thermal integration with solid oxide fuel cells, and we will listen from the coordinator what has been done and how this biogas SOFC system has been developed and the applications that it has. Jan, the floor is yours. We can already see your presentation.
Okay, thank you very much, Eleni, and I hope everyone can hear me properly. So thank you for the introduction. So you already mentioned this was a project about using biogas resources in solid oxide fuel cells. So it was a call from 2018 and it started in 2019, initially foreseen as a relatively short project with limited budget, but then as it was also said before, COVID also interfered and caused lots of delays with hardware because it's a hardware intensive project as well. There is additional funding that's been injected from several partners, the amount of which I don't know precisely yet because it's still ongoing. And we were 10 partners from 4 different countries, Switzerland, Germany, France and Italy. 2 stack supply partners, Solidera, Sunfire, 2 gas cleaning parties, Biocomp, Arol, 3 research institutes in addition to EPFL, Politecnico, Polshare Institute, Energia, CA, or 4 I should say, and then also EREP, which is a biogas, a specialized company. So the main objectives, this project was strongly concentrated on cleaning of the gas and developing along 2 lines. So one for rather smaller application targeting farms where sulfur has to be removed, the approach being sorbents. And there we are developing a site in Switzerland. And then there was also another development only working on the cleaning itself and going with a new high-risk approach of deep cooling of the gas to remove also sulfur, but also siloxanes. And they are targeting then larger sites, typically could be large farms, but also large municipal solid waste biogas producing farms or even also landfill. And so there's a range of objectives that were involved, the cost projections, reaching high electrical efficiency, and of course a lot related to the contaminants in biogas and testing with them. So in terms of KPIs, so here these are general KPIs for small mid-size power systems in terms of capex, in terms of durability, in terms of efficiency, which are all achieved in, let's say, in projections, but also partly in testing in the project. But then we had also very project-specific KPIs that are all related to the pollutions, the cleaning, and also dry reforming because of the specifics of biogas containing already CO2 as a reforming agent. So we first started by laying out a system and including this target of not having to supply an external water source. So that implies recirculation of the anode exhaust, and we did this in 2 ways, either cooling, condensing the exhaust, and then in this way moving to a dry reforming approach, or a hot recirculation where then we mix fresh biogas with also steam and CO2 from the exhaust, which has not been removed, and this is then a mixed reforming. And we did this for both Solidera and Sunfire systems that distinguish themselves by the operating temperature because they're electrolyte and anode supported stacks. So it's 750 and 850 degrees. So there's a range of sensitivity that has been taken into account, the reforming temperature, the fuel utilization, the recirculation ratio. And we identified, in all cases, we identified a range of conditions where high efficiencies can be achieved with both systems. And this then defined for us, for the rest of the project, set us 4 gas compositions for testing. So one dry reforming based, one mixed reforming based, and then also 4 Sunfire and Solidera type stacks. So it's about biogas. So we also had to assess what contaminants we're actually going to test with. So lots of work has gone into this, based on literature, but also from on-site measurements on a range of different sites. So a database was created here, which is available as a supplementary info here to this paper that was published. It contains up to 200 trace contaminants, and this paper actually is very recent, but is actually already very well cited, so it has an impact. And so this set us a choice of contaminants for testing. In addition to the classic H2S, also other sulfur compounds, dimethyl sulfide, thiol, methyl thiol, and COS, also in a realistic gas matrix, and not just as mixtures, and also not just as a single contaminant in, for example, only hydrogen. So likewise, lots of studies were done on sorbents. Also here a database has been compiled. In terms of testing, 21 different sorbents were tested from different suppliers, and to do this in a realistic gas matrix. So a total of 85 tests have been performed by 3 different labs. And this then allowed us to deduce from this test campaign how to approach a particular site, depending on the contaminants that are there, because we have identified sorbents that are good for certain contaminants. And we found out that, for example, COS is quite a difficult one to remove. And this then led us to the design of a cleaning system, sorbent-based, which you can see here. It's also published in the recent paper, and you see the approach in the green box, where we first take out H2S from the wet raw biogas, then we condense, we dry the gas to improve then the absorption of DMS and COS on other specific sorbents. I cannot go in detail in all of the other tests that were conducted because there's too many to report, but we did lots of testing on reformer catalysts, on cells, and on stacks. I just show you one example here of a stack that's actually still ongoing from Solidera, where we are poisoning it with dimethyl sulfide at different levels. We see the typical quick reaction of a stack performance to sulfur poisoning, that there is a fast drop, but then it continues on stable. And if the pollutant is removed, the performance actually practically fully recovers, which is really good news. And by the way, this stack is running in dry reformed biogas, also showing stable performance in that gas. So then now we are equipping a pilot test on one side in Switzerland, where an SOFC is actually being delivered, and commission is probably presently ongoing. There have been delays, as mentioned before, for a number of reasons, but as partners we are committed to continue this also post project. The site owner is very interested, and Solidera is interested, and we have designed the system in such a way that it would be easy in future also to exchange new sorbents that are cheaper and that we can also test in different campaigns. Then another approach, which was very ambitious, has been entirely designed and developed by Biocamp in collaboration with Politecnico, and this is then for large scale cleaning based on this cooling, as you can see here. So there is liquid methane is used in a reverse Stirling engine cycle for deep cooling, -70, even down to -100 degrees of biogas to precipitate H2S and siloxanes and part of the CO2. This has been assembled. This has been delivered. It is now on site, and it is also being commissioned. And this is going to operate on 100 cubic meter per hour gas flow rate. The cycle, of course, has a certain consumption, but it remains within acceptable, let's say, limits, and also cost-wise, as a first prototype with still potential for cost reduction, it fulfills the targets of the cost of the cleaning that had been set at the outset. So here some more pictures. So here you see the actual system delivered on site with the WASTEWATTS logo and poster there. It's been supplied to Vilnius, Lithuania, which is actually a customer from Biocomp. The biogas contains a lot of sulfur, contains also some siloxanes. Presently, this site has an enormous OPEX cost because it uses sorbents, and so it hopes to reduce this OPEX cost by testing this completely novel system. And also Biocomp again here is committed to continue this test for the next year. So in terms of exploitation, so this last site is actually a business case directly for Biocomp, who's also filing an international patent. The smaller previous site that I've shown, we also intend to run it for 2 years, depending on also some additional funding. As mentioned, we want to test different sorbents there. It is basically low OPEX, low CAPEX, and easy to dismantle as a site. Solidera is now looking for a digester company to team up to offer complete solutions for biogas SOFC in the range of a couple of 10 kilowatts, which is interesting. And in terms of expected impact, so this cryo cleaning is pretty novel as a new solution for cleaning large biogas flows. We definitely have much more insight also on sulfur cleaning requirement. We defined this more accurately, and the solutions that were developed are actually also quite generic. So not only for fuel cells, but also for biomethane injection, for the engine themselves, and also for catalytic reactors. We evaluated in detail market potential, and we think that 50 kilowatt is a nice size. And we also did a quantitative evaluation for the 4 partner countries and come up to a potential of 100,000 units in this power scale. Finally, in terms of risks, so this cryo cleaning installation is definitely a high risk, but with a high potential reward. We hope that results will be positive. There was a risk with the small scale demo in terms of the funding, so we really downsized and minimized the hardware cost that we can still go ahead with this testing and exploit it and have also a real impact there in the coming years. Sulfur cleaning remains a challenge. We have to go down to a ppm, so we also, thanks to this project, came with new ideas, alternative methods to sorbents, using sorbents. Biogas remains also a complicated field. It has to be regulated, it has to be simplified, and farmers have to be supported. And then finally, with this project, we are going a little bit against the mainstream current thinking, which is using biogas to separate out CO2 from it to go for biomethane and to inject it into the grid and to do large scale, which is then basically going to be used somewhere for heating. We think this is a pity because it leaves still a lot of biogas unused, which is in agriculture, which is in farms. We think 50 kilowatt makes a lot of sense. Obviously, digester cost has to further come down, and also SOFC system cost has to come down. But then with these systems, we can deliver winter electricity, which we think is definitely a lot of added value. Thank you very much for your attention.
Thank you very much, Jan, for the very interesting presentation. Indeed, a project that theoretically started as a small project, but it was since the beginning very ambitious. And being the project officer the last years, I know that you have put a lot of effort in this. So I think that your commitment and the high risk that you have taken, it will at the end indeed be awarded, and that you will have, let's say, the results from the demo that you expect. So thank you very much for the presentation. Before moving to the next projects, I would like to let the participants know that as it was done this morning, also through Slido, they can pose their questions. by using relative section on clean heat and power. They can pose the questions through Slido, and then at the end of the presentation, we can discuss some of them. We are moving a bit from the fuel cell area, and we have the pleasure today of welcoming in this pillar, in this area on the end users clean heat and power, the two new projects that we have on gas turbines. So back in 2022, we had published the topic on dry low NOx combustion of hydrogen enriched fuels at high pressure condition for gas turbines applications, and under this topic, two projects have started in 2023, and the coordinators from this projects, they will let us know how the projects have been evolved in the first months of implementation and which are their ambition. We will start with flexibility for hydrogen, and we will hear from Andrea Ciani. The scope and the ambition of this project. Andrea, the floor is yours.
Good, thank you very much. So let me just share the screen. So you should be able to see it now.
Yes, it's fine.
Very good. So thanks again for the introduction, and good afternoon to all the attendants, and welcome to this short overview of the Flex for H2 project, flexibility for hydrogen. So the Flex for H2 project is responding to the call, as just said, dry low NOx combustion of hydrogen enriched fuels at high pressure conditions for gas turbine applications. It started at the beginning of this year, back in January, and we successfully completed so far roughly 25% of the activities, actually in line with the original project plan. The total project budget is of 8.7 million euros, with a EU contribution of over 4 million euros. And in this project, we have also an additional support from Switzerland with roughly 4 million Swiss francs. So the project is focusing on decarbonizing very large gas turbines for power generation. And we could summarize its scope into three main areas. So first, the hydrogen combustion system design and development, aiming at a safe, efficient, and highly fuel flexible system to burn hydrogen in a premix clean mode, so exploiting actually sequentially combustion, thus with low emission and no diluents, aiming at the high firing temperatures of H-class engines, actually machines capable of providing power, electricity actually to 500,000 families, each machine. Second, the validation of the system at full gas turbine operating conditions. And ultimately, the development of pathways for the exploitation of the project results, thus a firm contribution to the EU Green Deal towards decarbonization of the overall electric power sector. So the consortium is composed of 9 partners organized in 6 work packages and led by Ansaldo Energia. So the work package 1 drives the combustion system development overall, while work package 2, led by Sintef from Norway, in close cooperation with Serfax in France, is after the advanced numerical modeling essential for the development of the combustor as a pool and its own parts, as well as the operation concepts. Work package 3 is led by the Zurich University of Applied Sciences in Switzerland and focuses on the thermoacoustic optimization of the system, while work package 4 covers all the testing and validation activities together with the German Aerospace Center DLR. Then we have work package 5, led by ETN, the European Turbine Network, which covers the communication and dissemination aspects, and in particular the exploitation of the results, leveraging also the inputs from the Italian electric utility Edison. And ultimately, work package 6, led by Ansaldo and Arctic Innovation, is integrating overall the work packages together and ensuring proper project management of the whole flex for H2. So let's have a look now at the project progress, focusing on actually one of the most important indicators, which is the amount of hydrogen that the system can cope with. Again, remembering here we are designing a low emission, no dilution combustion system for high firing temperatures. So the state of the art at the project start, so up here, could cope with up to 50% volumetric hydrogen in natural gas. The target at the project completion is to have the full flexibility from 0 to 100%, which is actually in line with the SRIA 2030 already. The main development steps include numerical simulations, which then feed the optimization of then prototypes that are manufactured and also fully instrumented for proper characterization of the performance of the new technology features, to ultimately test the new design and its operation at full engine conditions. And we can get a bit of feeling about the massive required hydrogen infrastructure in the image down here. As of today, we completed successfully the first design iteration out of the 3. So this loop will be a feedback loop that will make us grow and enhance the capability of the technology. So we completed just last month the first iteration. So we are at roughly 30% of completion of the project in this level, and we already could have the system capable to work with any blend of hydrogen and natural gas, including 100% hydrogen, but keeping the full firing temperature up to 70% hydrogen and having some derating for 70 to 100%. And by the way, 100% operation in the rig, we had it just 2 weeks ago. A second important parameter and target of the project deals with ignition, which, due to the very different boundary conditions and the challenges, is treated independently from the normal engine operation, like the one we just saw in the slide before. At the project start, the maximum allowed hydrogen in natural gas was again underlying we are here in a highly premixed low emission system and without dilution, was 20% as maximum at the beginning of the project. The tests are carried out in a different infrastructure. We see here a rig at atmospheric pressure conditions, fully reproducing then a real ignition sequence. And on the front, the system already achieved the capability to be ignited with the full range of hydrogen and natural gas blends, including pure hydrogen, which is actually the ultimate target of the project. So here we can try a short video, which is actually showing the ignition procedure. We are having the torch in the center, also operated just with pure hydrogen. One can see the neighboring burners that are lit again on 100% hydrogen and without any overheating or stability issues, which is exactly the target of having a stable and reliable ignition. Thus, on the ignition front, the project is already toward its full achievement. Some further work will look after the integration of this ignition procedure into the overall operational structure of the machine, of the engine. So the exploitation plan of the project covers the following 5 exploitable results. So improved combustor design for 100% hydrogen operation, hydrogen combustion prediction methods, looking also forward and then further optimization and further developments of the system, mitigation concept for stable combustor operation, so for a realistic implementation into the engine environment, validated full-scale combustor prototypes, and the technology roadmap that we were already mentioning at the beginning of the presentation, with the clearly associated impacts that are the contribution to a net zero pathway, the acceleration of the transition phase, new combustor technology, efficient grid balancing, which is a key element actually to allow also larger amounts of renewables to be integrated into the energy mix, and reutilization of the existing assets. Very important element to underline here is that the development is carried out within the constraint of a retrofittable system, so to exploit also existing machines that are running nowadays on natural gas, so that they can also be converted into hydrogen. So the communication activities of the project span from marketing activities to various types of publications and organization of conferences and workshops. The project developed a communication package with a leaflet, poster, and roll-up, aiming at an effective communication of the project scope, structure, and targets. All of them downloadable in the project website, where also further information is available, including project news and a list of events. So regular updates on the progress of the project are also available on social media like LinkedIn. So Flex4H2 was already present at the ETN annual general meeting and workshop back in March, and in the 11th International Gas Turbine Conference last month. Flex4H2 recently also appeared in the ETN quarterly newsletter with an interview about the project, reaching about 1,700 recipients. Last month, an article was published on the renowned Gas Turbine World magazine, and now we are after some 10 months into the project, and then significant results are being achieved, and we just submitted 3 article abstracts for the upcoming ASME Turbo Expo. And with this, actually, I'm reaching the end of this short overview of the Flex4H2 project. I hope I could give some flavor about it, and looking forward to further discussions on the topic. I would like to thank all the project team and the consortium for the successful progress so far, and of course all of you for the attention. Thank you.
Thank you very much. It seems that you had an impressive kickoff or a dynamic kickoff of the project. I hope that you will continue in this space, and that we will have also time at the end of this session to discuss a bit this interesting area that it was very recently included in the scope of our program. I will repeat once more that the participant can pose their questions through Slido. If your question is related to a specific project, please indicate this in your question. And after thanking a lot Andrea for his presentation, I will move to the next one, which is HELIOS project, one more project that we have on gas turbines. HELIOS stands for Stable High Hydrogen Low NOx Combustion in full-scale gas turbines combustion at high firing pressures. And we have with us Roy Hermanns from Eindhoven University, who will present the project and how the first months of implementation have gone so far. Roy, we see your presentation, and the floor is yours.
Yes, okay, was already too fast with the presentation. Okay, thank you for having me, and it is a pleasure to present the HELIOS project in this audience. So HELIOS project is similar call as the previous one, Flex4H2. So on stable high hydrogen low NOx combustion and full-scale gas turbine combustors at high firing temperatures. So the project is coordinated by Eindhoven University of Technology, and The call was in 2022. It's on the, as mentioned, dry low NOx combustion of hydrogen-enriched fuels. The project started a bit later than the previous project. In March of this year, we already started immediately with amendment because the bankruptcy of one project partner. So we had to fill this gap within the consortium, and with the help of the project officers, we succeeded in that stage. So the project will run for 4 years. I would say at the current stage, we're only at 10% of the implementation. So we're starting just a few months. The project volume is 4 million euros supplied by the Cleaner Hydrogen Partnerships. The partners are, as mentioned, Eindhoven University is coordinating the project. We have a strong industry partner, Energia, who is helping us, or now feeding us with the core flame sheet combustor that's needed for this technology. CCA, it's a research institute company in Italy. They support us in the, let me say, atmospheric large-scale testings. DLR, similar testing facilities, or probably unique testing facilities within Europe. So they are also involved in this project for the high-pressure testing, and Delft University for the experimental fundamental research. So that's roughly the core of the project. The goal of the project is, of course, to shift from natural gas to a hydrogen-based energy plant, and that's in a flexible manner. So the energy plant, electricity plant, should be able to run over a complete range of hydrogen contents. So not only natural gas, but also every step in between towards a green economy. So we don't have any CO2 emissions in the end, but in the end we have water emissions only. That's the ideal goal, the intention of this project, and in a brief summary. As I mentioned earlier, so our framework is around the flame sheet combustor of Energia, and there we try to build up a consortium around it, and every partner has its own tasks on the combustor development. That's the major task which has been implemented in this project, to run the combustor at all the required conditions when running on a gas turbine. We have transient conditions, so also the gas supply can vary over time. So the hydrogen content can shift in a mixture with natural gas. Also, the gas turbine needs to be powered up and has different operating conditions that needs to be taken into account in this project. And there we have the right partners on board on the turbine development, system integration and testing, and also towards the market. And then we're not working alone with this core of HELIOS project partners, but we have good support from our sounding board members. They are operating in the hydrogen production facilities, but also power plant development developers and end users which run such kind of power plants in the end. And they, together with them, we hope to make this project a good success. So what in the end does it mean? So one of the key aspects is the low NOx emissions. So low NOx means less than 9 ppm per volume. As you might know, NOx is in the Netherlands, for example, a high burden, in the sense that new facilities are a bit limited due to the expected higher NOx emissions, and you need to have really low NOx emissions to make a next step, because the industry is a little bit blocked in greening their facilities in the Netherlands in this respect. NOx is one of the aspects that's a huge burden in that sense. Then, as mentioned, it should be able to run at 100% natural gas, but also at 100% hydrogen, all the steps in between. And the high challenge is the high firing temperatures. So we have shown, or Thomson Energy has shown in previous project already, that they can run the burner at let's say gas turbine E-class conditions, but higher firing temperatures means also to go to high other class gas turbine classes like the F class. It's based on the flame sheet combustor, and we're aiming mainly as a retrofit option, similar as the previous project. And typical market range is between 1 megawatt and 500 megawatts. So that's really huge facilities that are aimed for. And the combustor will be applicable to all industrial and heavy systems like the Mitsubishi, GE, Siemens, as well industrial scale Opera type of gas turbines. Nowadays it's called Destinus. So project progress actions. So as I mentioned, we're recently started, so we're at 10% of the project total achievements. The table below I took from mainly from the strategic report from Hydrogen Europe, and yeah, it's mentioned the targets of 2024 and 2030 in that sense. So hydrogen gas turbine state of the art is 0 to 5%, 0 to 30%, depending on the mass of volume based. We have shown already with Thomson Energy a bit higher contents. But the target of HELIOS itself in the last column is shown that, as mentioned, 0 to 100%. NOx emissions should be lower than 9 ppm dry. And hydrogen fuel content during startup should be 100%. And that similar as a similar previous project, we're aiming for the same goals, as partly also reflected in the call text itself. Then if you include hydrogen in the system, you have a slightly penalty in that sense that your efficiency is a bit reduced, and we're aiming for less than 10% at 100% hydrogen content. The ramp-up rate is 15% load per minute. It's a bit higher than expected in the targets. And as I mentioned, also one of the critical aspects is the hydrogen content fluctuations. It's about 22% mass per minute. That's what we're aiming for in this project. So since we're pretty new in this area, so we're still developing and building up everything, also in the communication activities and so on. So the website is under construction at the moment, and we have already working and running a LinkedIn website. And we were recently we had visitors at the university from the European Parliament, and we were happy that we could present there the HELIOS project as a showcase to this ITRE committee. So that was very brief, the HELIOS project, and here the picture in the background, you show the participants during our last General Assembly meeting about a month ago. Thank you for your attention.
Thank you very much, Roy. I think we will have a bit of time. I really hope that you will stay all of our audience together in order to complete the presentation and also take one or two questions that we have in Slido, and one of them is related to the gas turbine. So thank you very much, Roy, and without further delay, I will go to base project pathway to competitive European micro CHP market, and I will give the floor to Alexandra Tudoroiu, head of policy in COGEN Europe, who will present to us briefly PACE project and the main achievement over the last years. Alexandra, the floor is yours.
Yes, thank you, Eleni, and I am very happy to be able to present this flagship project to you today. The project has ended in April this year. It's a project. It's a flagship project, a large-scale demonstration project that has taken quite some time to complete, but it has successfully reached its objectives. And this is not a small feat, given that given the unforeseen circumstances of COVID, of also the energy crisis that have impacted the project quite a lot. So when I say a flagship project, I mean from a certain perspective, the project budget, a 90 million project with a clean hydrogen partnership contribution of 33.9 million and a co-financing by the industrial partners of 56 million euro. You can see here the partners of the project. COGEN Europe coordinated the project. The project also involved the major manufacturers of fuel cell micro CHP systems in Europe, Wiesmann, BDR Thermea Group, Solidera, Bosch and Sunfire. And we were supported by research partners that were able to assess and analyze all the data that came from the field trial. So PACE at a glance, as I've already mentioned, we had 9 partners. The main objective of the project was to deploy more than 2,500 fuel cell micro CHP units across European countries, and to also have each of the manufacturers deploy at least 500 units with the objective to scale up production and this way be able to reduce the cost of the product. So then I will quickly, this is a very schematic way of explaining what fuel cell micro CHP systems are. These are fuel cell systems that are installed in buildings, either homes or small businesses. They produce thermal energy for space heating or hot water, as well as electricity that can be either used on site, mostly used on site, but also that can be supplied to the grid. And over the duration of the project, we've seen new products that were placed on the market from each of the manufacturers involved in the project, with 2 types of fuel cell technologies trialed. So both SOFC and PEM systems were part of the project. Also different capacities, so different sizes of the systems, either addressing the domestic target group or the SME target group. So we've had a range of customer groups as well, yeah, it's been interesting to see also several generations of products coming into the market by the manufacturers. So from generation X, Y, and even in some cases generation Z. So the objective of the project was to provide, to further innovate in terms of the product, but also to bring these products to market and show that they are mass market ready. So in terms of the high-level results, you can see here the that close to 2,600 fuel cell micro CHPs were installed. And as I mentioned, there were quite a lot of impediments with the COVID, with the project just in the middle of the deployment process, having been hit by the COVID pandemic. Nevertheless, the units were installed and monitored throughout all this period. Most of the units were installed in Germany, but you can see that quite a lot of units have been installed in Belgium, followed by France, Italy, and the UK, and several units also installed in Austria, 1 unit in Luxembourg, and 6 in the Netherlands. After the project, we see that the cost of the manufacturing of fuel cell systems has been reduced. We have managed with the PACE project to build routes to market for fuel cell micro CHP through installer training, marketing and sales development, in which the OEMs have been quite a lot engaged. As already mentioned, the installation and testing of new equipment for next generation systems. Having monitored all the units installed, the PACE project got data for 30 million hours of operation of the fuel cell systems. You can see here an overview of the scale up of the installations and their operation. More than 26 million kilowatt hours of electricity have been produced, and our colleagues from DTU have calculated that this is equivalent to the energy that can cook 35 million pots of pasta, just to put things into perspective. And this is a good foundation to actually be confident about the performance of fuel cell micro CHP units in a real life context. So based on this data, we see that the efficiency, the rated efficiency of the systems has been proven. All of the systems have an efficiency exceeding 95%, and 97 to 99% reliability. This means that the faults registered during the operation of these products have occurred in less than 1 to 3% of the time they've been monitored. As mentioned, more than 2,500 units installed, which is what the project, which was one of the project objectives, and 90% customer satisfaction. On the customer satisfaction, because this was really a project that looked into products that are placed in people's homes. PACE surveyed more than 1,700 field participants, and we've received quite good feedback from the users, with more than 75% of PACE trial participants having rated either positive or very positive several items in the survey: the product design, environmental impact, electricity generation, and comfort and warmth of the project. And we've also received quite favorable testimonials from the trial participants. Moreover, when it comes to the energy savings and the cost savings that are achieved by installing a fuel cell micro CHP in a home or a business, we see that 70% of customers experienced a reduction in their electricity bills following the installation of the fuel cell, with 34% saving more than 100 euro per month, or 1,200 euros per year. And this is quite an exceptional result because the data was collected during the COVID period and also during the energy price crisis. So even with gas prices increasing significantly, we see that fuel cell micro CHPs can achieve significant savings in the energy bills of customers. So then with the data that we collected as part of the PACE project, we also did some modeling to showcase the benefits of fuel cell micro CHPs. This is one example where a fuel cell, a heat pump, and a gas boiler were compared based on actual energy prices registered or collected in 2019, 2020, 2021, 2022. And we see that actually fuel cells perform quite well in terms of both CO2 emissions and annual energy costs, and even better when you have a combination of fuel cells and heat pump, which you see here in the left hand side corner of this chart. That's the magical combination where you get the lowest emissions and the lowest annual energy costs. So such an optimizing and mixing different space heating systems can actually have quite an interesting outcome in terms of the energy system, but also the customer benefits. I will not go into all the details here, but and you can find all this data on the PACE project website. But with the help of Element Energy, a partner of the project, we've assessed the customer case for a fuel cell micro CHP in different countries, taking into account the market conditions. And you can see here an example for Belgium, where a multi-family house installing a micro CHP fuel cell would actually see the lowest energy costs compared to a gas boiler, as well as compared to an air source heat pump, with payback periods being quite good compared to these two other technologies. And as mentioned, we have this modeling results for different countries and different archetypes of buildings. This is another example of the work that has been done as part of the project, where we're looking at different scenarios for the future for fuel cell micro CHPs, taking into account a range of hydrogen prices. We cannot know now what hydrogen will cost, or what green hydrogen will cost in several decades. However, we can see in which situation fuel cell micro CHP using hydrogen can be cost effective compared to other competing technologies. And there are many cases where fuel cell micro CHPs can actually be a good product in the context of hydrogen being used for space heating and electricity production. So in terms of the future scenarios and customer archetypes, we concluded that the installation of fuel cell micro CHP is beneficial in high energy consumers. The emissions can be impacted by electricity decarbonization, of course, but this can be mitigated, as we've seen in the other projects presented previously, by considering different scenarios or countries, also optimizing the system operation, replacing fossil gas with biomethane or renewable hydrogen, and also by taking into account the system benefits and the complementarity with heat pumps that we see as the main competitor or the main other option on the market today. And then in areas where hydrogen is available, fuel cell micro CHPs are seen as a strong alternative to hydrogen boilers because of the efficiency benefits and also because of their production of electricity in addition to heat. We also, with the PACE project, we were also able to showcase the European industry leadership in the area of fuel cell manufacturing. We've estimated that more than 200 million euro were invested by the European industry in stationary fuel cells over the past 5 to 10 years. This is quite impressive and it needs to be taken into account. As part of the PACE project, the fuel cell manufacturing capacity increased 500%, so increased 5 times. And also we see quite a lot of value added in terms of the installers that receive training and also in terms of the jobs created. We've also carried out quite a lot of dissemination activities throughout these years, culminating with the final conference of the PACE project that took place in April, and we've had quite a positive response to the conference and quite an excellent selection of speakers. And here you can see our other communication and dissemination activities. All of that is captured on the website of the project. That is a great resource for statistics, data, reports on that have emerged from the trial. So finally, why fuel cell micro CHP? It's a highly efficient home energy system that simultaneously produces heat and electricity. We see benefits in terms of consumer empowerment, supporting the European energy transition, providing flexibility to the energy system, and fostering innovation and high-value jobs. And I will end with some testimonials from the trial. We have a selection of interviews with the owners of the PACE systems. So yeah, that should be exciting to listen to. I was told that the technical assistants will run the video.
I don't know if our team can help us with that, with playing the video.
I can also give it a go, just to save time.
Yep.
Ik ben arts Mirjam.
Erik van den Einde.
Ik ben Ivan Stuyvens.
Ik ben Christoph Keulemans.
Mein Name ist Rainer M.
Mein Name ist Kai Thiel.
Mein Name ist Peter Merck.
My name is Joshua Grosch.
Wij maken dus onze elektriciteit zoveel dat we echt nodig hebben op een jaar.
Dus wij hebben toch een winst van zeker 40–50%. Ook over langere termijn kan men alles opvolgen, van week tot week, van maand tot maand, van jaar tot jaar. Kan men alles heel overzichtelijk op de app volgen.
De reden waarom ik die heb aangeschaft zijn eigenlijk uit overtuiging, ecologische overtuiging. En ook een oplossing te zoeken naar een alternatief naar zonnepanelen voor mij. Dus het is onbezorgd elektriciteit produceren. Het toestel op zich is een heel gemakkelijk toestel, ik moet er niet naar omzien. Maar om het alles bij te houden, zijn productie en zo, de chocolade interesseert me net iets meer als dat. Dus ik hou het zo goed niet bij.
Buiten de productie van elektriciteit heb ik ook nog een restwarmte. Die daarop wordt opgeslagen in een buffertank. En daar is ook een zekerheid dat ik tussen de 200 en de 250 liter warm water rond de 50 à 60 graden per dag kan gebruiken als sanitair warm water.
Wir haben die Anlage vorgeschlagen, weil die Anlage genau hierfür sehr gut zugeschnitten ist, weil sehr, sehr viel Energie verbraucht wird und die Anlagen erreichen hier die maximale Effizienz. Wir rechnen ungefähr mit 30% Energieeinsparung aufs Jahr gesehen dadurch.
Ich erinnere mich an das erste Gespräch im November 2021, als der Installateur hier saß und sagte, nun entscheiden Sie sich mal, wollen Sie eine Brennstoffzelle oder wollen Sie eine Wärmepumpe? Und ich dann fragte, warum eigentlich nicht beides?
The integration of the system into our house was the benefit, of course, of the system, because the system is actually, it's modular. So it has, I guess, 3 bigger parts, and also the installation was quite easy, comparable to bigger systems.
Okay, that was all from the PACE project. Thank you very much.
Thank you very much, Alexandra. Thank you for the nice overview and the results that you shared with us from PACE project. I know that you have a commitment in 5 minutes, so we can start already the Q&A session. Unfortunately, we will only take very few questions, and I would like to start with you. We have 2 questions that they have been triggered by your presentation on micro CHP. The one is about the competitiveness compared to heat pumps. It's an issue that you have thoroughly studied, I would say, during the project, instead of trying to hide, let's say, this kind of competition. And the second one is a more generic question about the micro CHP market, because in the last months we have seen some, let's say, traditional players or business focusing on micro CHP, unfortunately trying to shift, let's say, their focus towards bigger applications. So I would like to have from your side a general comment on the micro CHP market in Europe and the competitiveness related to the heat pumps. Thank you.
Yes, thank you as well. Indeed, we see that heat pumps have taken the center stage, given the context, more the geopolitical context, with the motivation we see to save energy and reduce the consumption of natural gas. Now, fuel cells, I would say, capex wise, they have similar they have a similar customer cost to a heat pump, or even lower. And then in terms of the annual costs of running a fuel cell versus heat pump, it really depends on the country. So countries where we see high electricity prices, I would say fuel cells would have a much quicker payback time than a heat pump. Whereas in countries, maybe let's give some examples like the Netherlands, where electricity prices have stayed quite low, and the spark spreads are low as well. Then perhaps heat pumps would have a better outcome there. But what we've seen also from modeling both heat pumps and fuel cells and gas boilers or hydrogen boilers, we see that a combination of the various solutions is definitely preferable to either electrify all or a hydrogen in heating scenario. So I would say that the answer is mixed. I cannot say that fuel cells are better than heat pumps or heat pumps are better than fuel cells. And then the micro CHP market in Europe, yes, it's been a slow segment in CHP to actually catch up. We were hoping that micro CHPs would by now reach mass market, but it hasn't been the case. However, I think that at least in the segment of domestic and SMEs, fuel cells are a very strong candidate because of their high efficiencies. And as we've seen in the testimonials, the customers that have them are quite happy, and they keep recommending it to their neighbors and their yeah. So I would say that within the micro CHP segment, fuel cells are quite a good candidate to actually pick up pace.
Thank you very much, Alexandra. I will move to two questions that we have now related more to gas turbines, and they are related to HELIOS project. I don't know if Roy is still with us.
Yes.
Okay, so one is about the system because that you will have for demonstration. The question says that that your system, that you have the combustion system is applicable from 1 megawatt to 500 megawatt turbines, and what is the size targeted for the testing demonstration of the technology?
So testing I don't know exactly the values of the burner that Thomas Energy wants to test at in the facilities at DLR and CCA. Typically, you have in such a gas turbine, you have multiple of these combustors located, and the concept itself, so flame sheet concept, has various ranges in that sense. So I'm not sure what exact power class they want to test at the moment. Yeah. So that's it.
And the second question is related to the temperature that you are targeting.
Well, as I mentioned in my presentation, we are aiming for towards the F-class gas turbine conditions, and that means that you're having inlet temperatures of the turbine of about 1200 degrees. But yeah, temperatures within a gas turbine, you have to know what high firing temperatures means in that sense. So that's typically related to the inlet temperature of the gas turbine.
Mm-hmm. Thank you very much. And the last question, I don't know if Andrea wants to react on this as well. It's a more generic question on gas turbines. And there is argument saying that we should not burn hydrogen, but we should only use it on fuel cells. Is there a room for both?
Yes,
I think
I think it's a discussion that is it's popping up from time to time, or actually often, and of course fuel cells are an excellent technology combined with hydrogen. But my opinion is that there is indeed a room for both, or actually I think even that the competition or the conflict between the two it's minimal, if really existent. So I think there was a discussion also this morning. There is not one technology that will make it all, in particular during the transition. So I think for smaller application where cost is also not the driver, for sure fuel cells would be an excellent choice. But when we are talking, for example, the integration with renewables and the need to produce large amount of energy, we were mentioning or was showing these gas turbines where we want to apply the flex storage to results is an 800 megawatt gas turbine that can go from 0 to its full power within actually matter of more minutes than hours. These are elements that are advantages that is very difficult to be replaced from other technologies. So the gas turbines, I think, when it comes to large amounts of power, large flexibility, the cost per unit of energy that is necessary to be achieved, so low enough for a large installation. This, I think, it's something where it's just a different market. We see also from an industrial perspective the customers that are asking this for these large gas turbines will not think of the fuel cell as an alternative solution, but not because the fuel cell is worse, it's just because it's a different technology for a different market and a different application. And I think then there is a second part that is a little bit more on the combustion, that I think the combustion is still perceived sometime as old-fashioned and dirty technology coming from coal, coming from diffusion combustion, diffusion flames that were often used a couple of decades ago, and of course associated also with large pollutants formation. But nowadays combustion systems are based on very different technologies and very clean. So this, I think, it's also maybe a second element that could create this perception.
Perhaps one thing to add from our perspective, but I think Andrea will support it also, because they are also looking in retrofit. So you have existing plants, electricity sites that need to get hydrogen supply in the future, and they have it takes a lot of depreciation time for them. So if you can retrofit them with hydrogen capable combustors, the majority of your plant will still be available. So it's an easy solution in that sense. Yeah.
Thank you very much for your comments. I think we will take only one more, and it's related again to the costs and related to remote projects. And I don't know if Massimo, you're with us.
Still here. Yeah.
If you see the solution becoming economically viable in the near future.
Yeah, the answer is for this type of site, yes, already now. We have, maybe it was not very clear in the presentation, but people can read the deliverable. In this type of site, like an island that can use the local renewable like wind and photovoltaics, the alternative to supply energy to this is to use a submarine cable, so a marine cable that has a cost that is not low, or to import diesel with a transport cost related to this. In this type of condition, this type of system based on hydrogen, so electrolysis, fuel cell, and storage, already now can be economically interesting. Same in remote area in the Alps, same in other. In this type of condition, maybe not in the center of Tourino or in the center of Basel, no. But in this area is already a good solution, even economically, apart all the discussion about the environment, of course, that, moves big amount of our effort in research. Yeah.
Thank you very much for the clarification. Unfortunately, we don't have time for more questions. I would like to thank all the speakers for sharing with us the results. All the presentations will be made publicly available. So if you have more specific questions, you will find in the presentations the links from the project, and you can contact directly the project. I would like to thank again all the speakers. Take, let's say, the main message that there is room, let's say, for all technologies, and I'm more in favor of seeing synergies, let's say, instead of seeing competitors. And I would like to thank everyone also for the good work that they are doing in their project and in order to move the technologies further in this area of clean heat and power. And with that, I would like to close this session, and thanks also the audience for their attention. Thank you very much and have a nice afternoon.
Thank you.